Welcome and thank you very much for joining us in this webinar today. I am Oscar Gonzalez from Word Electronics, and I will present to you today this fascinating topic, which is wireless power transfer. So the wireless power transfer systems come from a vision of a cordless world. Actually, we're already living in a cordless world. We count with Bluetooth, Wi-Fi, and other protocols for wireless data transfer. Nowadays, we can take a wireless headset, for example, and link it to our cell phones via Bluetooth, and then play a song, and it will transfer all the data needed to reproduce that song on the speakers of the headset, allowing us to move and walk away from the phone while we are still listening to that song. But what about power lines? I mean, is there a way that we can get rid of that too? Well, here comes a spoiler, sorry about that, but the answer is yes. In this webinar, we will talk about the findings of this field of application, the current standards, and of course, recommendations for you to design your own wireless power transfer system. And nowadays, a field of application for wireless power transfer is found in smartphones. Companies like Apple, Samsung, and Huawei have developed smartphones with the capability to charge their batteries by just placing them over a wireless power transfer station or a spot. Later, we will talk about the standards for comment. I would like to remark that these charging stations are based on a standard named Qi, which is currently, in fact, the most accepted standard for wireless power transfer. So this technology is already trying to get involved in our daily activities, starting with just charging the batteries of our cell phones. If we take a look into history, we will find out that more than 100 years ago, Nikola Tesla was in fact already developing this technology to power a light bulb. In the 80s, General Electric launched to the market an automated cordless toothbrush. So this is in fact a technology that was already considered since last century. It was until 2008 when the Wireless Power Consortium was founded, and it is in this association where the Qi standard is developed. In the last 10 years, we have seen applications of wireless power transfer in daily use devices, like smartphones, smartwatches, and even wearables. One of the most recent applications of wireless power transfer is in fact a charging station for EVs or electric vehicles. So as you can tell, this technology is being tested in many applications to encourage its development. So, as I said before, Nikola Tesla is in fact the pioneer of this technology. In fact, if we take a look at the drawing of his wireless power transfer system, we will notice that it is not too different than the designs that we use nowadays. He used alternate current in the primary side to generate a magnetic field around the coil. And he even implemented a capacitor to compensate the inductive reactance of the coil, and then reduce impedance of the primary circuit. The secondary coil needed to be placed near the primary coil to link to the magnetic field, inducing on it an alternate current that powers the secondary circuit, turning on the light bulb. So that's pretty much, in few words, how this experiment that Tesla did work. And in fact, regarding industrial applications, the wireless transfer of energy is useful to power devices that need to be completely sealed. For example, cameras with the capability to immerse in water need to count with the cover completely sealed to avoid water flowing inside the camera. So a wireless power charger is in fact a really good option for this type of applications when we want to immerse a device in water or in any other medium. Regarding medical technology, it is not too different. I mean, devices can be properly sanitized if they are fully sealed to avoid fluids getting inside the devices. In the automotive area, we count with in-car chargers that can charge the battery of a cell phone by just placing it over the charging panel. And regarding furniture or infrastructure, there is also current development in this field. They are trying to install like the in-car chargers, but in furnitures or on tables. It's just like that to charge any device that will be compatible with that wireless power transfer spot. So let me talk about a little bit the applications from some of our customers. So I would like to talk about first about the company Coil that has developed a sound processor to help people with hearing problems. It comes with a battery and a charging receiver coil that allows to charge the battery with a wireless power charging station. In fact, here in Word Electronics, we design small receiver coils for low power applications like this, where the size is in fact critical for the application. Another of our customers, Heinrich Wakekamp, developed a diving computer that can be immersed in water. It is, in fact, completely sealed to avoid water to get inside. In the design stage, it was considered that the best way to avoid fluids getting inside the computer was integrating a wireless power transfer system. So in this way, they could just charge the device by just coupling it with the power transmitter coil of the charger. And just like in the previous example, the receiver coil provides the coupled energy to the charging station of the battery of the computer. And of course, there are plenty of applications that can implement a wireless power transfer system. Low power applications, or even kitchen devices like coffee makers or blenders. Nowadays, regulations and standards for high power applications are being developed. They are looking forward to a possible integration of wireless power transfer systems to this field of application. And in fact, talking about high power applications, BMW is developing a charging system for electric vehicles, just like the ones used in the smartphones. They are trying to replicate the way these smartphones are charged by using a charging station or a spot to charge the device, or in this case, the receiver coil installed inside a car. Their goal is to charge completely the battery of the car in 3.5 hours, and it will be just a matter of positioning the car over a wireless power transmitter station to let the receiver get the energy and then charge the battery of the vehicle. So let's talk about the most important considerations to develop a wireless power transfer system in applications like this. The first one, wireless power transfer coils need additional space in the device. Of course, there are small coils available in the market, but still these components occupy more space inside the device than a simple power receptacle. In addition to that, circuitry is needed for power management and proper signal treatment of the output from the receiver coil to supply energy to the whole circuit of the device. Placement and distance from the transmitter coil to the receiver coil is limited. The coupling factor decays if any of these conditions is not properly addressed. Additional radio approval, so regulations need to be implemented and accepted to be able to develop wireless power transfer systems without any kind of risk. And of course, it represents a cost adder depending on the solution. So in order to design any wireless power transfer system, first we need to know how wireless power transfer works. In this case, the power is transferred via inductive coupling at short distances. It is in the millimeters range. So as you might know, when an alternating current is driven through a bovine, it generates a magnetic field that flows perpendicular to the flow of the current. So since this is a phenomenon that occurs in the near field, the secondary bovine needs to be located near to the primary bovine. Therefore, due to Faraday's law, the current will be induced in the secondary bovine that will flow through it. So being able to power any load connected to the terminals of the secondary bovine, just in the picture that we have, just like the picture that we have on this slide. To achieve this, ferromagnetic plates are placed behind both coils. And these plates help to direct the magnetic flux. So we need then most of the flux to flow over the side of the coil and not behind it. So in this way, the system is able to concentrate the magnetic flux to avoid any kind of leakage and improve the coupling between both coils. So in regards to wireless power transfer systems, two technologies are the most relevant in regards to this type of systems. The first one is the inductive power transfer, which needs one transmitter and one receiver to work. Its way to operate is like a transformer. Both coils are positioned close to each other to let the receiver link the magnetic flux of the transmitter, and in this way, power the load attached to it. Misalignments as well as angular displacements affect a lot the coupling and the efficiency of these systems. In the other hand, we have the resonant power transfer. In this type of systems, one transmitter can feed more than one receiver coil. The transmitter side operates at its resonant frequency, working like an antenna. And any receiver near the transmitter can link to a portion of the magnetic flux if they are tuned at the same frequency, allowing all the receiver coils to catch other regions of the magnetic field. So in order for a wireless power charging system to work efficiently, the frequency of both transmitter and receiver is required to be tuned to the same frequency. For different inductance values of charging and coupling coils, other associated parts of the circuit need to be changed as well in order to get the same resonant frequency. So let's take a look at these images. In fact, they show the devices that we have designed to demonstrate how each technology works. The load of both devices are LEDs. These LEDs turn on when the coils are close enough to link and let the power transmission to work. One of the main objectives of wireless power transfer systems is to develop and accept a standard for wireless power transfer designs. By following a standard, plenty of devices will be able to work with any wireless power spots. So this is in fact something that will encourage the acceptance of the wireless power transfer systems in the market. Nowadays, there are two standards very accepted by designers to develop wireless power transfer systems. The Wireless Power Consortium works with the Digi-Key standard, which is based on inductive power transfer. Power transfer uses a resonant tank at very low frequency, between 100 and 205 kilohertz, over short distances in the range of millimeters. In 2009, in fact, they developed a standard for low power applications of 5 watts, and it was until 2016 when this standard was extended to power profile of 15 watts. Currently, the Wireless Power Consortium is looking forward to a high power standard, because nowadays they only count with the power profile up to 15 watts. So let's talk now about the air-fuel aliens. This is in fact based on resonant power transfer, in which the receiver coils are loosely coupled to the transmitter. Power transfer uses a resonant tank at very high frequency of 6.78 megahertz over long distances. This distance is approximately 40 millimeters. It comes with the advantage of charging multiple devices at the same time, and its capability is up to 30-watt systems. But in fact, at the beginning of this decade, there were many standards trying to dominate the market. In 2015, the most accepted standard was not defined yet, since the Wireless Power Consortium and the Air-Fuel Aliens developed good standards for different type of technologies to transfer the power wirelessly. As I just explained, the Wireless Power Consortium offered an inductive power transfer standard, and the Air-Fuel Aliens was more into developing systems based on resonant power transmission. In 2018, the Digi-Key standard from the Wireless Power Consortium was the most accepted by designers. The key of its victory was in fact the development of smartphones that implemented a wireless power transfer system to charge their batteries based on the Digi-Key standard. In fact, for every device and application in the market, safety is always the key. So regarding wireless power transfer, we need to make sure that the wireless power spots do not harm people. It does not matter how cool this technology is. If it harms humans, then it has nothing to do in the market. Also, it is important to assure that the wireless power spots do not damage phones, credit cards, and other sensitive devices to the magnetic fields generated by the coils. So pretty much we need to protect people and we need to protect electronic devices from these fields. So regarding approvals, we can divide them into two. In one end, we have the regulatory tests, which are in fact mandatory. The devices that come with a wireless power transfer system need to pass the tests to be able to be launched to the market of a country. In the other hand, we have the certifications, which are in fact private requirements. The Wireless Power Consortium Digi-Key certification is a test that proves that the device is well designed and that it works with all other approved devices. And if you're wondering what is the acceptance of the wireless power transfer systems, we can see its growth in this chart. These columns show the Digi-Key certified phone charging system shipments. So from 2017 to 2018, there was an increase of 2 times the Qi certified wireless phone charging transmitters. And in the same period of time of 1 year, there was an increase of 68% of the shipments of Qi certified wireless phone charging receivers. So as you can see, this technology is being implemented in more devices and applications year by year. Also, you need to take in consideration that there are many cars in the market that come with an integrated in-car charging panel for compatible phones. So these cars comply with the Qi certification, most of them. So any Qi certified smartphone is capable to be charged by just placing it over the power transmission spot. So let's take a look at the coil system requirements. To design a wireless power transfer system is very important to consider the coil's requirements. So first, we need to determine what is the power level of the application to base the design on the correct guidelines and the standards. The receiver device needs to be designed to integrate the receiver coil and its circuitry inside. Also, the distance between transmitter and receiver is in fact a critical factor. So it is important to design the transmitter and receiver devices to have the less separation possible between the coils. The less distance, of course, the better. We need to consider as well the positioning of the receiver device to make sure that the coupling of both coils is as high as possible. The electrical performance of both coils and their compatibility is very important. The quality factor of the coils, compensation with capacitors, the DC resistance, and the shielding are just some considerations that need to be double checked to make sure that our system is in fact efficient. And of course, last but not least, the price is an important parameter too. So the less expensive, the better. Let's take a quick look at the proximity effect and the skin effect because they are very important when we talk about coils. So skin effect and proximity effect are two physical effects caused by eddy currents inside a coil. They are related to the frequency of the current driven through the coil. So the higher the frequency of operation, the more increase of impedance. It can be influenced positively by using Leeds wire for the coil. In fact, high quality Leeds wire reduces the DC resistance and the area of unused copper, increasing the performance of the coil. So, as you might tell, the higher the quality factor of the coil, the better. As it was explained before, that the freedom of positioning is an important parameter to consider in a wireless power transfer system. Let's take a look at these options that we have. If we use a transmitter from the left side, for example, the receiver's Z-axis needs to be perfectly aligned to the Z-axis of the transmitter to link the most portion of magnetic field. Any misalignment will decrease the coupling factor of both coils. However, the transmitter from the right side of this slide allows us to move the receiver device along its surface without having coupling issues. The implementation of each transmitters depend on the application, of course. Let's say that the charging device is a smartphone. Then we can implement a charging spot on a table using the transmitter from the left side, since the phone will not move once it is placed over the spot. However, if we want to place the phone over an in-car charger, the phone will move while we are driving due to changes on speed, for example. So a panel can be implemented with the transmitter from the right side just to make sure that the phone will be charged even if it moves along the panel. The coupling is in fact a key factor for the wireless power transfer systems. This factor may be affected by lateral misalignments, angular misalignment, and vertical misalignment. In this case, neither lateral misalignment nor angular misalignment are permissible in wireless power transfer systems. The vertical misalignment needs to be as small as possible. Let's remember that the vertical misalignment means the distance between the transmitter coil and the receiver coil. So good coupling and maximum efficiency of the system also depends on the size of the effective area of the receiver coil in the magnetic field to make sure that it links the most portion of the magnetic field. A coupling factor of 1 is ideal, meaning that there are no losses at all. But we know that this cannot be possible. However, the wireless power transfer systems accept a coupling factor between 20% and 95% to consider them, in fact, effective systems. And as it was explained before, the angular misalignment affects a lot the coupling factor. In the graph, we can in fact visualize its decay due to the angular misalignment of the coils. Let's picture the best scenario ever. If both coils are parallel to each other and the distance between them is minimal, I mean 1 millimeter, the coupling factor of this system achieves up to 95%. It is a really good coupling factor. Otherwise, in the worst case scenario, if there is an angular misalignment between both coils of 40 degrees and a separation of 10 millimeters, the coupling factor decays to a bit more than 10%, which means that the system is not efficient to transfer power wirelessly. So now, let's talk about how coupling factor and efficiency relate in these systems. As I explained before, the coupling factor depends on the positioning of the coils. The quality factor is a number that describes the performance of each coil. It represents the ratio between inductive reactance of the coil over its DC resistance. Or in other words, it represents the ratio of reactive losses over DC losses. So the lower the DC losses of the coil, the higher the quality factor. If we take a look at the formula, let's take a look at it. If we take a look at the formula, we will notice that coupling factor and the quality factor are very important to determine the minimal loss factor. We can notice that the only variables involved then are the coupling factor and the quality factor of both coils. The bigger this product, which is named figure of merit, the lower the minimal loss factor. This means higher efficiency for our system. So just to summarize, the coupling factor is influenced by positioning of coils, and quality factor is in fact influenced by the performance of the coil. And the higher these values, the better for our system. So let's talk about the improvement by using the ferromagnetic shielding that most of the coils come with. By using ferromagnetic shielding, we can increase the coupling of the wireless power transfer system. Without the shielding, the magnetic field dissipates in all directions over the coil. If a ferromagnetic shielding plate is placed on one side of the coil, the magnetic field can be directed only over one face of the coil. So therefore, we can control the direction of the flow of the magnetic field with ferromagnetic shielding. In the simulation located at the right side of the slide, we can see how the magnetic flux density measured in Teslas is focused in a small volume between transmitter and receiver coils due to the ferromagnetic plates placed over and under the coils to concentrate the magnetic flux, allowing us to transfer more energy wirelessly. As it was explained before, coupling factor is a key factor in this type of systems. And in fact, it also depends on the coil size ratio. We can see three examples of coupling factor between one transmitter coil and three different receiver coils with different areas. The receiver at the left has, in fact, exactly the same area as the transmitter, and the coupling factor between both is a bit more than 80%. However, if we take a look at the receiver coil located at the right side of the slide, we can notice that its area is half of the area of the transmitter, and so the coupling between both is barely 61%. This happens due to the lack of effective area of the receiver to link the magnetic flux that the transmitter is generating, causing an equivalent leakage inductance in the system. So from the previous slide, we can conclude that the most similar the effective area of both the transmitter and the receiver coils, the better coupling factor for our system. If you're looking for coils to fit in your design, you can make sure that we can assist you to find the best option for your system. We count with a wide range of coils in the market for different levels of power. In fact, we can provide you coils from 5 watts to 400 watts, or we can even look for the possibility to customize a coil for you. You can make sure you can reach your direct worth representative to know the details about customized coils. And in fact, we recently developed, in collaboration with Infineon, a 200 watts development kit with data transfer. The applications of this kit are plenty, but some of them are drones, robotic lawn mowers, and also power tools. Also, you can use it for IoT and devices in a medical environment. Some characteristics of this kit are that by changing the resonance frequency, the output voltage can be regulated. It is also scalable from low to high power. I mean from 10 watts to up to 10 kilowatts. The MOSFET's switch is close to the zero crossover point, so it can achieve an efficiency of more than 90%, and data transfer from receiver to the transmitter is possible. And in this way, we can achieve a better management of the power of the system. Of course, we count with application notes that you can consult to get more knowledge in regards wireless power transfer for the industrial environments. I truly recommend you to take a look at the application notes we have available for you on our website. It can provide you lots of information and, of course, help with your new designs. And of course, we also count with a development kit of 15 watts. This kit was developed in collaboration with Renesas. Some characteristics of this kit are that the power transfers wirelessly up to 15 watts. It supports bi-directional data communication. So it enables device authentication and system data transfer all in one. Some applications of this kit are found in the smartphones, also tablets, headsets, and portable devices used in medical applications, since all of them are low power applications. Of course, we count with a dedicated section in our website for wireless power transfer. Here you can see all that we can offer you to develop your designs in this field of application. So I definitely recommend you to take a look at it. The mix and match table is in fact one of the most useful tools we have to count with to help you out to choose the right coils for your system. In fact, in this mix and match table, it shows you if the transmitter coil that you have chosen for your system matches any of the standard receiver coils we have in the market. It also shows you the voltage and power level that each coil was designed to. So you can quickly select the coil based on these parameters and then check the different options of coils you have to match the one that you have chosen. Also, we count with our great tool, which is REDEXPERT. It is able to help you to select the right coil for your design. It is able to provide you information of the performance of the coil and of course the performance of the entire system based on the different test values, like the frequency of operation, for example. It can even assist you to calculate the value of the capacitors to do the proper compensation for inductive reactance of the coils and definitely increase the efficiency of the system. You can even select one of the transmitters and see the ratio of coupling it has with the different receiver coils we have available. Definitely, we count with a book about this field of application. Our book, Trilogy of Wireless Power Transfer, contains information about basic principles of these systems. It comes with design tips and also applications. So I really recommend you to purchase it if you're interested in this field of application. All that we know about wireless power transfer systems is in fact contained in this book. So it is a really good investment if you're interested in developing this technology in any device that you might have in mind. And finally, just to summarize, these are the success factors of wireless power transfer systems. So the first of them all, no metal contacts, so no wires are needed. It also allows us to develop completely sealed devices. So we can design any device we want. We can implement a wireless power transfer system in order for us to immerse that device in any medium. There are standards that can guide us to design an efficient wireless power transfer system. And of course, the standards are the key. They allow interoperability of different devices. So you can design a charger for a smartphone, but you can make sure that as long as you design it based on the Qi standard, it will be compatible with the smartphones that were designed with an integrated receiver coil based on the Qi standard. Of course, we always need to look for safe systems that do not harm people or electronic devices. Again, if the system harms people or any electronic device, it has nothing to do in the market. And of course, IoT. IoT is a field of application where this technology can be developed and implemented, since it is focused on developing sensors, embedded systems, and wearables, and more. Many applications of IoT come with batteries or even supercapacitors. So a wireless power transfer system is in fact a really good option if this device will be exposed to the environment or if the conditions around the device are not ideal. So we can seal the package and just use a wireless power transfer system to charge the supercapacitors or the battery of our IoT device. Nothing is more powerful than an idea whose time has come. I truly believe in that the time for wireless power transfer systems has come, and right now, we have the opportunity to develop it and make it happen. Thank you very much for attending this webinar today. I really appreciate that you have been here, and I hope it has been helpful for you. Now we will be glad to take a look at some of your questions. So remember, of course, you can always get in touch with your direct Worth Electronics representative if you have any questions about this technology, or if you would like to order some coils for your designs. So let's take a look at the questions. Oh, in fact, this is actually a really good question. What is the amplifier recommended for the transmitting circuit? That's a really good question. Well, first of all, the RF amplifier topologies are not suitable for wireless power transfer systems because their operating efficiency is too low. Let's remember that one of the objectives of wireless power transfer systems is to have as low losses as possible, because a portion of the energy will be lost due to the wireless transmission of energy. Regarding amplifiers, the Class E amplifier is in fact the most popular amplifier topology for wireless power transfer systems. It is really simple and it comes with a high operating frequency. Also, I would like to remark that the amplifier needs to operate at a fixed 50% duty cycle due to the ISM band restrictions. But let's think about other type of amplifiers. As I remember, also Class E amplifiers as well as other Class E amplifiers are recommended for this type of applications as well. So any of these two classes is in fact highly recommended for this type of systems. Let's take a look at other question. Of course, if you have further questions about any topic, you can always reach your Worth Electronics direct representative. Let's take a look at them. What is the maximum frequency that Litz wire can be used at? That's a really good question as well. The Litz wire, it is in fact designed for frequencies over 1 megahertz. The Litz wire is in fact a really good option if you're developing a wireless power transfer system based on the air-fuel aliens. You know, these aliens that use an operating frequency of 6.78 megahertz. That is in fact one of the purposes why we have developed Litz wire. Otherwise, if the frequency is under 1 megahertz, any regular coil made out of copper can work for your design. You will not experience any more problems with it. So let's take a look at other questions. Okay. If I do a compensation with capacitors, how do I connect them in the circuit? That's a good question as well. Actually, I mean, you can take your capacitor and you can connect it with the coil either in series or parallel. I mean, it doesn't matter. Of course, each one has their own properties, but any configuration is going to work for your system. But definitely the way to calculate the capacitance will change in each case. The recommendation, or well, the configuration that we will recommend is to connect each capacitor in series to the coil. So in this way, you can calculate the capacitance very easy. I mean, if that's the case, if you're using a series to series configuration, you just need to consider the leakage inductance that you will have on the loop, as well as the mutual inductance that both coils will have. This will help you to determine the value of inductance in that loop by taking in consideration the leakage inductance and the mutual inductance. Also, of course, you need to know the value of the frequency of operation that you will use, either if you're based on the G standard from 100 to 205 kilohertz, or if you're based on the air-fuel aliens of 6.78 megahertz, for example. Or if you do your design not following any of the standards, of course, you can use any frequency of operation you want. But pretty much, let's focus on these standards. With this information, I mean, you already know the total inductance on your loop, as well as the frequency of operation. You can calculate the proper value of capacitance to compensate the inductive reactance of the coil, and then reduce the value of the impedance. I mean, you need to look for the way to reduce the reactive portion of the impedance to just have the DC resistance as the total impedance of the loop. So I hope that answered your question. That is definitely the most recommended way to connect the capacitors because it is one of the easiest ways you can calculate the capacitance of each one. Let's take a look at other question. Let's take a look at them. So when the transmitter has multiple coils, are the coils frequencies synchronized or are they oscillating independently? Well, actually, if that's the case, I mean, if you're using a wireless power transfer station or a panel to power more than one receiver coil, you need to make sure that they are all synchronized. As it was explained before, um, you, when you resonate the circuit of the transmitter, you're going to be able to transmit the energy a little bit longer than if you just use it without working on its resonance frequency. In this case, you will need to make sure that the resonance frequency of your receivers match the resonance frequency of your transmitter, because otherwise the power that you're going to receive on each receiver is going to be very low, and of course it will not provide enough power to your application. I mean, let's remember that a portion of the magnetic field that is going to be generated by the transmitter is going to be lost, or it is not going to be able to be linked to the receivers. So we need to make sure that they are in resonance just to make sure that they receive the most amount of energy. Let's take a look just to see if there is any other question. What efficiency of energy transfer you may achieve for the transfer from 100 to 150 watts in the demo kit for up to 200 watts? All right, that's a good question. Actually, I mean, we did some tests, and in fact, the efficiency of the system is approximately, if I'm not wrong, between 80% and the 95%. It is in fact a really good efficiency for wireless power transfer systems. In fact, just a quick comment I didn't tell you during the presentation. The coupling factor of this type of systems, they usually go from 0.2 to 0.95%, but the efficiency, in order to consider the system effective or to consider them efficient, it is around from 80% to 90%. So pretty much we need to take a look at the efficiency that the system will have. But yes, our kit counts with an efficiency of around 80% and 90%. Let's take a look at just to see if there are any other questions. What is the typical ferrite type used to shield the coils? The permeability value? That's actually a really good question. As I remember in the data sheets, that information is not shown. Pretty much the ferrites that we use to shield our coils, it needs to be. I mean, the intention of the ferromagnetic material is to reflect any magnetic field that might fall on it. So just to direct all the magnetic field over the coil. The exact value of the permeability of the ferrite, it depends, of course, on the coil. But also, I mean, I'm not sure about a specific or a rated value for these ferromagnetic materials. I can definitely contact you over email in order to answer that question. For the rest of you, definitely if you have more questions or if you need any assistance in your design, you can always make sure that you can reach your direct work representative. They can get you all the assistance that you need. And of course, we can get you the coils that you might need for your design. So from my part, that's it. Thank you very much for attending this webinar today. It has been a pleasure to present this fascinating topic, which is wireless power transfer. Thank you so much for attending, and please stay home, stay safe, and stay healthy. Have an excellent day. Bye-bye.